group here, and specifically on the work we are doing in discovering and characterizing inorganic materials. And by inorganic materials, I mean non-alloys. So we will not talk about alloys. They're very important, certainly, but that's not the topic of today. And we will also leave organic crystals apart.
Report in progress.
Oh, that was not me. So I will talk also a bit about machine learning. We are using machine learning already for quite some time. We'll just talk about a part of our developments on machine learning, especially the ones related to discovering new inorganic materials with our big models, okay? But of course, this is just a small part of what we are doing. So this is the outline of my talk. I will first discuss material discovery, what that means from a theoretical point of view. How can we discover materials? Then I will tell you about all our developments in machine learning in this respect. And then I will give you some examples. We don't have much time to go through examples, but I will talk. I chose superconductors as a specific example of the topic that I like. But we'll get there. Okay, so very general introduction. How important are materials? So we can argue that materials are the most important thing in the human development, right? We even name our historical eras after the materials we use. So we all know this. We had the Stone Age, the Bronze Age, the Iron Age. We can discuss that there was a Steel Age, right? Because we don't really use iron as it is anymore. And many people say that we are in the age of silicon. I don't think it's actually true that we are in the age of silicon, because if you look, for example, at the mobile phone, that is the symbol of modernity, right? It's the smartphone. You realize that there is certainly a lot of silicon, but there is essentially every single element in the periodic table is inside the phone. Actually, some estimates indicate that we have 70 different chemical elements in the mobile phones. So essentially everything is used in electronics, and the mobile phones in particular. So I think it's reasonable to say that we are not in the age of silicon, but we're actually in the age of the periodic table. Yeah? So essentially every single element that is stable is relevant nowadays. Okay. Oops. So the problem is that not all chemical elements are born equal, right? There is a very big difference in abundance between the chemical elements, and there is also problems of toxicity and environmental, the extraction of some elements also very, very problematic. And this is a periodic table from the European Chemical Society that actually tries to indicate this. So you have the green elements are the ones that are fine, plentiful supply, at least for the needs that we have. So you see thorium here appears as plentiful supply because, I mean, we're still not using thorium nuclear reactors, so we don't need thorium, so it's fine, right? But you see there's a lot of red and orange around, and I want to bring your attention just to a couple examples, okay? Hello? Okay. So there are two hand-picked examples. One of them is lithium here and cobalt. You all heard about lithium batteries. They also include cobalt, at least the ones in the mobile phones and the laptops. Lithium, I'm not particularly worried about lithium. The biggest reserves are in Bolivia, but that's fine. But cobalt has been considered by the American Mineralogy Institute to be the most difficult chemical element to replace. It's used, for example, in hard drives, and there's very little cobalt on Earth comparatively to the other elements in the first row. The other example is neodymium dysprosium. They are used to make this iron neodymium boron magnets, and a windmill has, so to generate electricity, has something between 200 and 400 kilograms of these two elements, one windmill. Now, neodymium, again, is not the most concerning, at least for me. It's dysprosium. Dysprosium is 10,000 times less abundant than neodymium, and the magnets don't work without dysprosium. So if you want to have an electric transition into green energy, you have a problem here that very few people discuss. right? You don't have cobalt, neodymium, or dysprosium. So what are we going to do? Well, we can use copper, but that's another story, and that's also very problematic and less efficient. So this just to tell you that we have problems, material problems, and that we need new materials clearly and alternatives in many, many different areas of technology. So how do you find these new materials, right? Until now, it has been trial and error, essentially. So experimental synthesis is difficult. It's time consuming. Of course, in the end, that's what we have to do, right? But we all know that this is a very time consuming and expensive path, right? So what we as a community have been proposing for the past maybe 10 or 15 years is a different path. Is that we try to combine ab initio methods with high performance computing and now machine learning to try to find out these new compounds that are potentially stable and synthesizable and that are useful. Because unfortunately, most of the compounds are not really useful for anything, but there are some, you know, some exceptional compounds that are. So that's what we want to do. We want to use computers to comb through millions and billions of possible compounds and try to find something that can be synthesized and useful. So our general strategy is actually a little bit different from most of the community. It goes in this way. So we actually try to find all possible stable inorganic compounds. That's the first step. So we first screen for stability, because obviously it's something that is not stable and that's not synthesizable, it's useless, right? And then after we know which materials are stable, we scan for interesting, I call them extreme properties, right? And there's a reason for this strategy, is that, and this was very surprising for me when I realized this, there are not so many inorganic compounds that are possible. Thermodynamics poses an enormous constraint in inorganic compounds, and it turns out we cannot make so many. So the largest database that we have, that is ICST, only contains around 50,000 materials, inorganic materials. If you compare it with chemical substances that are stored, for example, in the registry of the American Chemical Society, they have 100 million, more than 100 million entries. So it's not saying that it's we are doing much less than the chemists, right? It's just that thermodynamics for us is a very big constraint, much bigger constraint when you think about solids than when you think about molecules. I think there are around a few thousand compounds that are added to ICST per year. In the American Chemical Society database, it's, I think, around 6 million substances a year that are being added. So this gives you an order of magnitude. There are not so many. Yeah? It's a number that is perfectly within computers nowadays. So this is what is known. Now we can try to extrapolate, and maybe what is possible is maybe a factor of 10. Okay? Maybe there are 500,000 inorganic bulk compounds that we can. Sorry? Yeah, these are the ones we know. No, there are 186,000 in ICSD, but most of them are the same composition, are just different experiments of the same for the same compound. And this is it's a number that is a bit misleading. So if you go and check what are the really different materials that are inside, there are around 50,000 around. So most of the other things you have, I don't know, 20 different experiments for silicon. Yeah, which is obviously useful information, but it's less than one thing. Then the other thing that I find very important is that by knowing the distribution of a certain material property, we can actually define what extreme means. Because if I ask some of you what it means, for example, a material with an extreme, I don't know, volumetric density, what is it? What is the number that defines it to be extreme? And these adjectives are used in a very loose way in the literature. And you can only know what extreme means or what large or normal means by looking at the distributions. And I will show you some distributions. Then, finally, our current theories, even if they have their limitations, are actually good enough for most materials and properties. Okay? and we will interpret our prediction statistically, because we have an error, and the error, as all errors, is random. So we cannot say this material has an error of whatever, because if we knew the error, we also knew we would also know the exact value. So the only thing we can give is intervals of confidence and things like those. Okay, that's the approach. So let's, first of all, how do we determine the stability of a compound? Stability is a very complicated word. There are different kinds of stability. I don't want to enter here. We will mainly look at something that's called thermodynamic stability. Thermodynamic stability means that if a compound is thermodynamically stable, it cannot decompose in an infinite amount of time to other compounds. Why? Well, to explain you why, I just drew here a phase diagram. This is a very simple phase diagram. It's a binary phase diagram. We have compound A here, B here, and this is formation energy. Okay? So in this case, AB2 has the lowest formation energy. This is stable. Yeah, but AB4 here is also stable because it cannot decompose into a linear combination of AB2 and B. That would be a straight line. I'll show you an example here. So this is what I mean. If you have a compound that is here, for example, this is also stable because if it would decompose, the energy would be on this straight line. So it would be here. This is lower in energy. It cannot thermodynamically decompose. As simple as that. It's the compound is here. So if you have this composition and the energy turns out to be there, obviously it can decompose just into a linear combination of this one and that one. Okay, it's just very simple energy argument. Now, this line that you see here is called the convex hull thermodynamic stability. So for a binary, phase diagram is just a line. If you think about the phase space of all possible compounds, it will be a hypersurface in this 100-dimensional space. Okay, that's in the end what it is. It's convex. Mathematically, you can easily see that it has to be convex. Yeah.
It seems to me that metastable compound, which could be there all well, but really interesting and important. You're ignoring all metastable compounds.
Yes and no. We'll go back. I will come back to that afterwards. Okay, it has to do. One has to be very careful with also the energy, the orders of magnitude of the energy. I will come back to that. So the distance to this line is actually a measure of thermodynamic stability. As what we're saying, obviously we can synthesize unstable compounds, obviously. But if you look at statistically, it's almost impossible to synthesize something that is 100 millieV per atom above this line. Okay? We don't know, so if you grab all known compounds and if you calculate the distance to the hole, I think 95% of them are within 100 millieV per atom from this line. And the other ones that are not are probably mistakes. Yeah, so incorrectly determined structures or structures that will determine at high pressure and that are calculated at zero pressure or something like that. So keep this order of magnitude in mind. 50, 100 millieV per atom, there is a good chance that you can synthesize things. More than that, the probability decreases exponentially. Okay, as simple as that. The scale here, you see, it's 700 millieV. You will see that the scale is actually larger than that. I will show you that. So typically, we calculate our energies with density functional theory in perfectly standard ways. Okay, we can discuss also the errors afterwards if you want. I don't think this is important. Okay, let's start to discuss the way we discover materials, and let's go step by step. So there are kind of two completely different paradigms that are used. The first is that we keep the stoichiometry fixed. For example, let's say we have sodium chloride. I have an atom of, I have a part of sodium for a part of chloride, and I try to find the minimum of the potential energy surface, and this minimum will be stable, dynamically stable structures. So this is actually a very complicated problem from the mathematical point of view. It's a global optimization problem, but this is done. It comes into the heading of global structural prediction methods that are now used in different areas. They are very good in the sense they are thorough and unbiased. So you give it a composition and it tries to find out what is the minimum energy structure, okay? They are unfortunately computationally very expensive. We have done a lot of calculations using structural prediction. I just put here some examples from materials for hydrogen storage to high temperature superconductivity at high pressure. Actually, the great success of these superconductors at high pressure is not really the superconductivity part, it's the structural prediction part, because they were all predicted before they were synthesized, and they were predicted using these methods. Now we can, for example, predict grain boundaries, the microscopic structure, the atomic structure, grain boundaries, defects, point effects, and so on and so forth. But this is not the topic of today, okay? The topic of today is the second paradigm. That is exactly the opposite in a sense. In this case, we will keep the crystal structure fixed, okay? So we will choose a structural prototype. I don't know, the A15 compounds, for example. And we will search for the compositions, for the chemical compositions that are stable in this configuration, okay? This is known as prototype search, also known as component prediction, depending on who you ask. This is relatively fast because we don't have to search to do this global optimization problem in the potential energy surface. Of course, the problem is that the prototype has to be known, okay? We have to know the structure beforehand. To show you that this works, we go back a little bit in time, something we did a few years ago. Because when we started, we looked at perovskites because everybody likes perovskites in physics. Actually, that was the main reason, but they have exceptional properties. I think you all know that. I don't have to go. So the composition of the simplest perovskite is ABX3. And in physics, we believe that X is usually a non-metal, oxygen, sulfur, and so on. It turns out that this is actually not the most common case. The most common case is when B is a non-metal. There are many more of systems like this than normal perovskites. So they're called anti-perovskites when B is a non-metal. They're called perovskites, normal perovskites when X is a non-metal. But anyway, and they often crystallize the deformed version of this ideal cubic 5-atom cell. 5-atom cubic cell, that's easy, right? So we just run them all. So there are around 500,000 possibilities, and then the unit cell is relatively easy. We can actually run them all. I will not show you all the results because it's a bit too much. I will just show a very special case that are these nitride perovskites. So you probably never heard about nitride perovskites because they actually didn't exist. And we just tried for curiosity. And what we plot here is the distance to the convection of stability. So you see the scale, it is 0, okay, green. Red is more than 400. This actually goes to 4 electron volts, so 4,000 milli-electron volts. And you can clearly see that if there are nitride perovskites, they are here. And you will see, so here you have something like lanthanum or calcium or whatever. Here you will have something around tungsten, okay? This is the green region, okay? This is the only region where you can have, of composition space, where you can have a nitride perovskite. So we went a little bit further. So I have a zoom here for the lanthanum, when A is lanthanum. And it becomes quite clear. Maybe you can have lanthanum, molybdenum, nitride, lanthanum, technetium, nitride, maybe not a very interesting compound. And with the tungsten and the rhenium and maybe osmium, those are the most likely ones, okay? We did a little bit more calculations. We found out that, so around 23 compositions were promising, but most of them actually were, in the end, they would decompose, distort to something that was not a perovskite. So our conclusion is that only 3 compositions could yield a nitride perovskite. Okay. Now, this was in 2015. We published this paper. I asked a few experimentalists around, they all told me it was very hard. But to my surprise, last year, 2 of these 3 predictions were actually synthesized. This was, the first one was lanthanum tungsten nitride, it was a science paper from an American group, and also lanthanum rhenium nitride synthesized. And we were actually very happy that we also got the prediction of the crystal structure correct. And these apparently are exceptional materials. So they have, they're polar, they're piezoelectric, and they seem to be quite interesting. But this is not my work. Of course, this is the work of the experimental groups. Now, I showed you perovskites, but we have a problem, right? So the quest for new materials in this way has a combinatorial curse. So here's an example. Let's take an intermetallic compound, a ternary intermetallic compound. There are around 60 metallic elements in the periodic table. Let's take 60. And we know from 200 years of experiments that we know around 1,400 different ternary intermetallic structure types. The average number of atoms in the unit cell is around 14, which is quite a lot to do millions of calculations, right? Now you just write down the number of combinations just for intermetallic ternary compounds with this 1,400 combinations, and you get to this number. If you try to calculate all of them, you could wait a few tens of thousands of years. So we have a problem. We cannot do this, right? However, as I told you, thermodynamics is very important, and most of these combinations are highly unstable. So the number of reasonable intermetallic compounds is orders of magnitude smaller than that. So we have to find the needles. That's the idea. And here comes machine learning, okay? As I told you, we are just going to do machine learning in this case to accelerate by orders of magnitude our DFT calculations. That's the idea. So what is the strategy? As always, we start with the materials database, right? I will discuss this afterwards. We train a machine. I will discuss also the kind of machines we are training. And then the machine, just given a certain crystal structure and stoichiometry and chemical composition, will predict an energy or any other property, okay, that we know. We just filter them, the energies in this case. We validate, so we go back to the DFT to have a better estimation of the stability. And then the ones we like, we go to our friends and tell them, here's something interesting or not. Okay, that's the, please search here. That's now, we have to look at this carefully. So first of all, we need data. We have actually already in my group, we have more than 1 million DFT calculations, so 1 million compounds calculated. We combined it with the 2 other databases that were using more or less the same parameters because we have to make everything compatible. So we had to eliminate the duplicates and be sure that everything was compatible. And in the end, we got 2.4 million data points that are the data for us to train. For you to have an idea, this is the distance to the convex hull of these 2.4 million compounds. And you see it goes to 4 UV, okay, more or less. Yeah, so we are looking at this here. All temperature can stabilize by 10, 20, 30 millieV. Yeah? Defects can stabilize by 10, 20, 30 millieV. So you see everything that you can do, even with temperature or defects or whatever, is here. This part is useless.
That's a quick question. So you said before there are only 50,000 compounds.
No.
So these 2.4 million, are these 2.4 million unknown compounds?
Most of
Oh, they're all theoretical. Oh, the people are predicted.
No, I mean, there are also the 50,000 experimental ones that are also included.
But these 2.4 million just simply calculation results from DFT or something.
You just make a combinatorial, you just search, for example, all 500,000 perovskites, or all 500,000, or all chalcopyrites, or all whatever, right? And you build a database like that's what most people were doing.
But these are like stable theoretical compounds.
They are stable dynamically, or at least we hope. This means that they are minimum of the potential energy surface. But thermodynamically, they can be extremely unstable, of course. So this is our starting data. Then we had to represent the crystal structure in a certain way in order to be fed into a neural network. We are using, actually, it's the state of the art currently. We use what's called crystal graphs. So we transform the crystal structure into a graph where the nodes are the atoms and the edges represent, if you want, the bonds, okay? Now, of course, this has to be translated into some numerical data. We call them embeddings. So we need some embeddings for the different atoms and for the edges, but I will not bother you with that. Okay, so we have a crystal representation, crystal graph representation of our crystal structures. And then we have a network that works like that. So we have our initial embedding of the crystal graph. Let's say that these are convolutional layers. They're not exactly convolutional layers, but they are a series of layers that allow us to change this representation into another one that the network wants to use. So if you want, this is a better representation of the crystal structure for the neural network. These are, of course, layers of neural network layers, and they use some techniques that were developed for natural language processing. Okay, they use attention vectors and so on and so forth. Let's maybe not enter here. There's the pooling layer, and then there is what you all know, a normal, fully connected neural network. Okay, and this, if you want, this part here will try to improve on the features, on the representation of the data. This part will go from that, improves the representation to a property, the energy, the gap, whatever you want. For you to have an idea, we have around 62 million parameters. So 5 layers with around 11 million parameters here, each one, another million here, 4 million there. For comparison, GPT-3 has 175 billion parameters. This is the best natural language model that exists at the moment. It cost, I think, $50 million to train. And I will show you that our 62 million parameters work. So for fun, I could say that natural language processing is actually much harder than solid state physics. Okay, so this is our network. And we trained the network and we used it to predict stable compounds. Okay, so we went through a series of prototypes, most of the prototypes that were known actually for binary ternaries. Quaternaries are still not done, but we are going through that also. The space of possible compounds that we scanned, so it was 1 billion, around 1 billion ternaries and 13 billion quaternaries. So we just generate these compounds, pass them through the network, and see if the network tells us they are stable or not. In the process, we actually found 26,000 compounds on the hull. So the previous hull, the hull that comes from ICST, has 20-something thousand compounds, but I will talk about that again. And we found a new 250,000 compounds within 50 milli-electron volts per atom of the hull. So these are all compounds that we have some hope, or let's say the probability of being able to synthesize them is relatively large. So our current database is 3.4 million compounds, so we did an extra million calculations, and we have 80,000 materials in total that are thermodynamically stable. So just to put this into perspective, the orange slice was before we started. So our hull had the 43,000 compounds. These are the thermodynamically stable compounds. And many, and the part of this are already predictions from our group from before. And we found another 49,000. So we essentially doubled the knowledge, our knowledge of stable inorganic compounds in the last year or so. Now, what? Yeah.
Predictions. And so within that, there must be the 50,000 known inorganic compounds. So you predict all the known compounds. How many of the known compounds are in that? Have you predicted?
So the known compounds here are less than 50,000 because 50,000 includes more than one stable phase, one or more than one known. For
said 50,000 at the beginning.
Those are, so in the whole, on the whole, I think there are a bit less than 30,000 from experimentally known compounds.
Percentage are included in.
They are included in it. So they're included in the orange. I know it's the other way around, sorry. They're included in the, I said it the other way around, sorry. They're included in the blue one.
The way you said, oh, these are known from experimental structures. These are not theoretical predictions. It's in blue.
Both.
Oh, so you automatically include them.
Yeah, so the experimental ones are around 30,000 from this. So there are another 20,000, more or less, roughly speaking, that were already theoretical predictions. And now we added another 46,000 to our convex hull. Yeah.
I also have a question. So where did you get your training data set? Did you look at all the literature ever produced? How did you train your
It's easier than that because, so first of all, we had a lot of what we call high-throughput studies that were done over the years. So we had studied already a series of prototypes. I can give you a list if you want, but they were perovskites, chalcopyrites, dilophocytes, sodalites, and so on. So we have more than 1 million calculations ourselves, and there are online databases that you can just use the data. So we mixed all that thing together, and that was our start.
But some are experimental and some are calculation, but you train, do you weigh them differently or how?
No, not at all. And one has to be careful here because in particular here, where we want to decide if some material is stable or not. So experimentally, we just have information about the stable materials. But if you want to train a machine learning algorithm that will tell you this is stable, this is not stable, you also need to train it with unstable materials.
Yeah.
So we cannot, unfortunately for this, we cannot use only experimental data.
Ah, okay.
Because we will not only have the positive.
Got it. But the training, I guess the only thing you care about was the stability rather than maybe some other property, like you could put maybe piezoelectric.
You can train everything.
You can train, but here this was just focused on.
So what I showed you is just stability. We trained the machine to predict other things.
Okay.
I don't think I have this machine in particular. I don't have other results here, but
okay.
If you have data, you can train it.
Great. Thank you.
So so just as a parenthesis, this does not include only bulk, but also includes 2D materials. So we have, you probably never saw these things in your life. They are actually stable or close to stable 2-dimensional materials that came out from the computer. And I find particularly amusing this kind of structures that if you think a little bit about them, you will see that they are precursors of quasi-crystals that were discovered across the street. So we believe actually that there may be a lot of surprises still in the 2D world, but this is just a parenthesis, okay? So what do we want all this data for? I told you we were searching for stable materials, and then we have to give the second step that we want to search for materials that have some interest. So I will just give you some examples, and I will not at all be exhaustive because we have done this for many properties, of course. Let's start with a very simple one. Mass density. So what is the densest material that exists? I put the answer here, actually. It's plutonium, which is not very interesting, I would say. Maybe, so excluding plutonium, and the densest material that is known are iridium osmium compounds. So osmium is known to be the densest element, one of the densest elements that exists. But it turns out that some iridium osmium compounds are actually denser than osmium itself. Now, this is just a curiosity, of course. I don't think it has, maybe it has some application. I don't know. Actually, can you guess what is the other side? The less dense material, the lightest material, again, inorganic bulk material that is known, that we know. Actually, I think it's experimentally known. Well, it's magnesium borohydride. It's here. So it's, this I think is not a prediction. This is an experimentally known material. Magnesium borohydride, they make a series of very, very open structures. And this is actually the structure that we, in our database, has the lowest volumetric mass density. And now, I mean, I discussed the two extremes. Let's talk a little bit about the distribution itself. And this, for me at least, was also a surprise. What is the 0.2 grams per cubic centimeter? I don't know. I will have to. These numbers are theoretical, and we have an error of around 8% in the volume in these calculations. So it should be, the density should be a little bit, its volume is too large. So density should be a little bit larger. Zero temperature problem, of course. Yeah. Now, I want to look at the distribution. This was a very big surprise for me. I mean, I was expecting Gaussians. Just maybe because we always talk about Gaussians and standard deviations and so on and so forth. All the distributions that we found, none of them looks like a Gaussian. None. This one actually goes quite rapidly to 0 on this side, but that's kind of clear because you cannot go beyond 0, right? But you see what happened here? Long tail. Essentially, every single distribution of every single property that we plotted has long tails, has fat tails, so Pareto-like tails. And this is actually very good news for us, because this means that we can find materials that have exceptional. So the tail are the materials with exceptional properties. If the distribution was Gaussian, and solid state physics would be very boring, right? Because the distribution would finish here. Yeah. As the distribution is polynomial, the tail is polynomial, actually, it brings that's what brings about extreme behavior and exceptional materials. Okay, in this case, again, as I told you, it's maybe not such an interesting property for us, but this is actually the case for every single property we plotted to now. Okay. Okay, let's go to a more complicated property. I chose superconductors. I could have chosen anything else. I don't know, whole masses. I could change of the band gap with the volume. We have looked at all the magnetization per unit volume. I mean, you can plot whatever you want at the moment. Let's look at superconductors. That it's a really non-trivial problem. And I will just discuss conventional superconductors. If you want to discuss non-conventional, we can also do that afterwards. But here I will just talk about conventional electron-forming superconductors. Those are the ones that we are sure we understand, and we can actually calculate with a rather good accuracy. And the motivation here is actually a technological motivation. If you look at the industrial applications of superconductors, there is one application that is by far the most important of all, that is generate magnetic fields. Now, LHC in CERN is using niobium-tin superconductors. TC, I think, is 8 or 9 Kelvin. Each dipole magnet in the LHC has 200,000 euros of niobium. Niobium, more than half of niobium on Earth is in one mine in Brazil. More than half. Okay? So, next application, ITER. ITER is using the new technology, niobium-3 tin. That is a material that is known since the 60s. TC is 21 Kelvin or 20 something Kelvin. The niobium again, right? Why can't you use any of the other superconductors, the high TC ceramics, the magnesium diboride, iron selenide? Why can't you use these things? It's very simple. They are brittle. You cannot make easily cables out of them. So they are used, for example, in leads or contacts, but they are not used to make cables. Yeah? So if you think that fusion is the future, we have a problem, right? We need superconductors. And we don't care about room temperature. If you are at 20 Kelvin, it's already not too bad. So we embarked last year in an endeavor to try to find an intermetallic superconductor that is not worse, let's put it like that, than the niobium-based superconductors, but that is not brittle. That's the idea. So this is just a plot of the elastic constants. Brittle behavior is here. Ductile behavior is here. So you see niobium-3 tin that is already quite brittle for technology is here. Magnesium diboride is there. That's why you don't see any NMR machine done with magnesium diboride. Okay, so it's as simple as that. Okay, so we started doing high-throughput calculations on our enormous database. So we filtered all the metals that had densities of states that were reasonable. We started by the most symmetric compounds to make calculations a bit faster. So when I wrote this, we had 2,200 metals done. Now I think it's around 3,500. This goes fast. And the objective is, of course, to study all. And here's the distribution of TC. And again, this is cut at 0 because obviously most compounds are not superconductor or have very, very, very small superconducting temperatures. And what do you see? Cut tail. Again, yeah? Even in conventional superconductivity. I will show you in more detail some of the results actually, but you see the scale goes to around 40 here. Okay, magnesium diboride is around 40 also. First surprise, we grabbed all the predictions we have with less, or all the results we have with more than 10 Kelvin, and we plotted the distribution of chemical elements. Has anybody guessed this? This apparently is the element that is most correlated with high temperature conventional superconductivity, nitrogen. I didn't know. And I think no one knows because it's complete surprise. Then it's obvious. Niobium, all these transition metals are obvious. Carbon is not a surprise. Transitional metal, boron is not a surprise. Hydrogen is here. There's a huge amount of people that are trying to find better superconductors at ambient pressure with hydrogen. Maybe they should look at nitrogen, right? That's the, so nitride. This was the first biggest surprise. Then we plotted our compounds. This was also quite interesting. So this is the logarithmic average of the phonon frequency. Here you have the electron phonon coupling constant, and the size and the color of the points is related to, is proportional to the transition temperature, superconducting transition temperature. There are some false positives here, actually, that came out that have instabilities, so that were not catched in the first round of calculations. That's the case of this compound here. It was a very big disappointment because it's actually a cuprate, and having a cuprate with the 40 Kelvin normal superconductivity would be quite interesting, but it's an instability. So this is also an instability. But we have here a funny one: lithium molybdenum nitride. Yeah? And we have other ones. There, for example, this is intercalated graphite or boron. Yeah, green is around 40 Kelvin. Around 36, 38 Kelvin. Yeah. And then these ones here are around 20. The yellow is a bit less than 20. Sorry, I should have put a scale. It is if you do two gap superconductivity. If you take the isotropic average, it's much smaller. It's half, 17 Kelvin or something like that. So this is just isotropic superconductivity. But as magnesium diboride is the only compound that we know where two-band superconductivity doubles TC, we're probably okay for most compounds, right? But you're absolutely right. So let's look at lithium molybdenum nitride just very quickly. This is the structure. These layers are isostructural to molybdenum diselenide or disulfide. So this is exactly the same structure. So you can get them just by replacing molybdenum by replacing the sulfur by nitrogen. Okay, but it's exactly the same structure. And then it's intercalated with lithium. You can think about the structure like that. This material is actually an experimental material. It was synthesized already a long time ago, searching for superconductivity. But theorists immediately did band structure calculations and realized that the band structure, the Fermi surface, I'm sorry, that is here, is not two-dimensional. There is this part here that is not two-dimensional. So they said, not interesting for superconductivity. Yeah. This is our calculation, gives 40 Kelvin. So apparently being two-dimensional is completely irrelevant. We also tried the same composition in the chalcopyrite structure, that is the second, let's say, metastable structure. We get 20 Kelvin. Now, there's just one small problem. This dip here. This is related, we think, to a charge density wave instability. If we are on one side of the instability or the other one, it's very hard to know. Yeah, we are certainly very close to charge density wave instability. That's the first problem. So obviously, if you have such instability, it will decrease the TC. The second problem is that experimentally, this was synthesized only twice. And the first time they claimed that they have alloying between the molybdenum and the lithium. And that again decreases the density of state at the Fermi level and will probably decrease superconductivity. Okay, but this is the kind of things that you find out just by searching, right? That is almost at the end. This is, I think, my last slide. I just wanted to show, because the people usually say, and they, with some reason, that machine learning doesn't teach us anything, right? It's just numbers, a black box. And I want to show you that actually one can use it to understand things. This is, again, superconductivity. We did essentially all the Heusler and all the anti-perovskite compounds. And there are around 1,000 of each that are stable in our calculate, close to stable. And this is omega log, so the histogram, and this is the electron phonon captive constant. And there are some models in machine learning where the model is a formula. So you basically give it data, and it tells you what is the formula that best fits this data. You can actually obtain Newton's equation using this method. It's actually very funny. So this is what comes out of this formula. So these are the formulas that best fit the data. This goes well beyond linear regression or quadratic regression. Of course, you see there are exponentials here. And I mean, the formula is completely free. And you can see, for example, that it's easier. Lambda is essentially proportional here, the square root of the density of state, here the density of state. You see that here, for example, the mass of the Y atoms, so of X, Y, Z, is preponderant, much more important than the other two masses, and the difference of electronegativity. So based on these formulas, I can easily understand the behavior of superconductivity in an entire family. Of course, this is an approximation, this is a model, but you can also learn things from easily from machine learning, not only predict numbers. Okay, so I hope that I could convince you that our crystal graph attention networks, as they are called, can predict accurately properties. I mean, I didn't bug you with the errors and all that stuff, but we can essentially reproduce TFT calculations just 1,000,000 times faster. That's the idea. That we can discover new materials. We still have some challenges. It's misspelled. Anyway, we have some biases in the data set. So our problem is not at all the neural network at the moment. It's the data. That there are still some biases present in the data, and so this translates to some problems then in the prediction. And of course, the accuracy of DFT, but we're also working on that, and many people are working on that already. Some better ways of doing things. Now, what we are doing now is this was still not the complete chemical space. So I believe that in the next 2 or 3 years, we'll have explored all the binary, ternary, quaternary chemical space. So we will have probably a large, more than half of all the compounds that can be produced. We will have them in our database. And of course, we will explore all properties that can be calculated. We are already doing that. Of course, many people are doing that. Anything that can be calculated can be accelerated with machine learning. A very interesting development that I think will really come in the next year or so will be thermal properties that will have access, give access to temperature phase diagrams, for example, or other properties like phonons or thermal expansion coefficient and whatever can be derived from it. And then another thing that will certainly come in the next couple of years by us or others, we have enough time and people to do it, are high pressure phase diagrams, because our knowledge of high pressure phase diagrams is really very limited at the moment. Okay, I would like to thank you and my people in Halle and my collaborators in Coimbra and Jena. And very quickly, just one thing, a disclaimer. The pictures that I showed you, the illustrations were actually computer generated, and parts of the abstract were also computer generated. Just for you to see what we can do now. This is generated by asking it to give me a picture of a chemist discovering materials in the style of impressionism, and an artistic picture. And this is a bit more complicated. Apparently, the model I was using didn't like robots, so it required a little bit of tweaking to get a robot out. Okay, thank you.
Thank you. I also had a lot of fun playing with GPT-3, like
Yeah, you can.
email to and anyway, so we have time only for one quick question. I'll just, because we're a little late.
Okay, we are delayed. Okay, yes, thank you. Very interesting talk. So I have questions regarding your prediction about the stability, thermodynamically and kinetically of the different inorganic compounds. But are you able to predict how this compound can be synthesized chemically?
So there is one very big problem. If there was data, for example, from high throughput experiments, if there was published data, for enough data, yeah, the answer would be yes. So for each synthesis process, if there was enough data, yes. The problem is that there is not much experimental data.
You don't know how the bond can be formed and
For that, they have to do
mm.
kinetic, for example, molecular dynamic situations for every specific problem. So not for a huge, I mean, one can specifically for some compound, we may have some answers, but not for.
And of course, for the, I don't know, do you need to develop a new theoretical code or method to predict these new compounds? Do you need to develop the new method theoretically or yeah, or new code to?
If you want to predict synthesizability?
Yeah, the stability, yeah, stability of the compound.
All these.
Or new structures.
Yeah. There is always some code involved, but the beauty about when you do machine learning is that you have all these wonderful libraries like TensorFlow or PyTorch or Keras or whatever that have most of the work already done inside. So this is actually easier. You don't have to develop an enormous amount of stuff to be able to do this kind of. You do need big graphics cards that you do need.
Okay, great. So let's thank Miguel again. And we'll switch to the next speaker.